Thank you. Okay, we have also the recording. So, going back to our, I don't know how to remove this. Oh, okay, going back to our transducer, the potentiometer. We have the basic circuit, the input tension, and then, as I said before, we are having that the output tension here. Let me call it EO. Give time. Yeah, it's coming. Okay, the output tension is somehow related to the unknown deflection, unknown displacement. Okay, that is related through mechanical system to the actual displacement. Now, let me consider that your let me go back here. Your transducer will be characterized by a maximum, okay, let's say total displacement that could be measured. So the scale of your transducer, okay, out of the actual, yes, be right now, okay, out of the actual available displacement, okay. And so what we are saying here is that this position here is related to the actual, okay, displacement that is unknown. From the practical point of view, what I can say is that your output tension, O, is linear related to the unknown displacement XA. Okay? And that's because you can say that the resistance of the potentiometer R is a function, linear function, because of the circuit of your actual displacement. Okay? Now, this circuit, this functional circuit is, the R is the resistance, and then is a linear function of the displacement X. That is, yeah. Now, this circuit, although very interesting, is, let's say, a theoretical one, because we need to know the output tension EO in order to have an estimate of the displacement. Okay, so in order to measure this output tension EO, you have to apply a measuring circuit. So this basic circuit has to be a little bit modified in order to take into account the measuring circuit itself. So I have to rewrite, redraw a new circuit so that we are closer to the actual circuit in reality than this one that is just theoretical one. So the actual circuit is just a one that is including an additional resistance of the measuring circuit overall. Okay, so let me rewrite that. So what I have to say now is write the previous circuit like this. Okay. Then what I got here is the previous, but now I have to add another resistance. This resistance is called Rm, resistance of the measuring circuit. Okay. Then we have once again the total resistance related to the maximum displacement. Here we have the actual displacement corresponding to the actual resistance that is characterized by your E0. Okay, E out, sorry, E output. Okay, we can see, and I'll prove it with you right now, that the ratio between the output tension and the input tension, let me call it X, is given by this equation. 1 over A over 16 M X A. Okay. That is your final equation. And this equation is telling you what's the relation between the output tension that you are going to measure, EO, with respect to the unknown deflection, XA. That is the actual one. Okay, that is your input. If you go back to the very beginning here, you would like to know what is your XA, okay, once you measure EO, the output tension, from your measured circuit. Okay, basic circuit is the one that is not including any measuring device. So this one, very easy. And for that, we can see in a few minutes that the relation between the output tension and the unknown displacement is linear. There is just one constant K to be defined. Okay. But in reality, when you are measuring your output tension, you have to modify your basic circuit like this in order to take into account your measuring device. This is the measuring device. Okay. Please note that just the measuring resistance is of interest for this circuit. So no impedance at all. Okay, it's no inductive, no capacity. Okay, equivalent inductor or equivalent capacity is of interest for this activity, for this measurement. Just the resistance. Okay. Now let's prove this. Okay, so I hope that you recall some information from electrical engineer, very basic, nothing special, but just let's play with the circuit now. Okay, that circuit could be rewritten from the electrical point of view as follows. So let me write the circuit with the input. A little bit more.
Yeah, and maybe just slow down just a little bit.
Yeah. Ready?
So in that equation, the RB is that
The potentiometer resistance, the overall. Okay. Okay, so let me, in order to prove that equation, let me rewrite that transducer operational conditions into an electrical one. So we have the input differential potential. Then what we got here is our resistance that is part of the potentiometer resistance, like this. And then we close. I can call this RA, RB, RM. So RM is the measuring resistance. RA plus RB is the potentiometer resistance. Okay. RB is the resistance when your cursor is at the actual displacement position. So it's the actual resistance. From the current point of view, what's happening? You are having that you are a current I. Okay. RP is the potentiometer resistance. No, RB, RA is what is left over with respect to RB. So that RA plus RB is the total potentiometer resistance. Okay. Please remember, I scroll up a little bit. Yeah. If you look at this, the upper part of the resistance is what I call RA, the lower part. So this is RA, and that is RB. The overall is RP. Okay. So RB is strictly connected to the position of your actual reflection. Okay.
And then what about HT?
It's the total displacement. Here is, okay. If you look here, the xt is the maximum displacement that you can measure. Okay. It is the maximum value of your transducer. Okay. Having said that, now from the electrical point of view, you can call the overall electrical current as I. This electrical current is divided into two flows. I call it IP, the current that is flowing through the potentiometer, and IM, the current that is flowing through the measuring device. Okay? Can you see it? Of course, what you're having is that I, the overall current, is the sum of the two. So IP plus IM. From the electrical point of view, then the differential of potential between these two nodes, let me call it node 1 and node 2, should be the same. So what I can say is that RB times IP is equal to RM times IM. Okay. And then finally, the overall differential of potential that is feeding your circuit, measuring circuit, okay, is so that the differential of potential between A and B or P or M just are the same, should be the same. So RA times I is equal to a plus, sorry. I plus R B I P is equal to the input tension EX. Okay. These are the equations that could be used in order to prove the previous equation. How can you do that? For example, starting with the second one, let me
For the third equation, so I guess why wouldn't it be like why couldn't it be-
because RA times I is the differential of potential at the resistance RA.
Right,
Okay.
right,
Plus the differential of potential at the resistance B,
okay,
that is RB times IP, should be equal to the input differential of potential, EX.
what about our measuring?
Oh, that's the same. I use
Okay.
that one. That's the
Okay.
same. They should be the same.
Yeah.
I already introduced that relation, the previous
Above,
equation.
okay.
Yeah.
So it's
Yeah,
Okay.
for sure. So let me use that equation, and I can say that your RA, sorry, not RA, that is, sorry. Okay, your IM is equal to IP, then RB over RM, just from the second equation. Okay, from this last equation, what you can say is that RA times IP plus IM and RB times IP is equal to EX. Can you see that? I make use of the first equation here. Okay. Therefore, what I can write is that RA times IP plus RA IP RB over Rm plus RB IP is equal to EX. Okay. So you can collect IP from that equation. And then what you got is that the current that is flowing through the potentiometer, IP, is given you by this ratio, EX over RA plus RA RB over RM plus RB. Okay. Once you have this information, the current flowing through the potentiometer, you have just to multiply this electrical flow current times the resistance in order to have your output tension. Okay. And thus your EO, the output tension, that is equal to IP times RB, is just equal to EX over RA over RB plus RA over RM plus 1. Now, the last link that we need is the connection between the electrical quantities, the resistances, and the displacement field, the displacement that I need to measure, to estimate. Okay, so remember, what you got is that from the very beginning, can you see it? What I got here? RA over RB and RA over RM plus 1. Now, if you go back to your notes, you can see that first, the displacement and the resistance, because of the configuration, are linearly related. Okay, so we can write that the overall potentiometer resistance with respect to the maximum displacement, okay, is equal to the actual resistance RB with respect to the actual displacement. Okay, thanks to the configuration that we are considering. And that is telling me that if you would like to have the information of the actual resistance, that is equal to RP times XA over XT. Okay, that is the actual resistance is a fraction, okay, of the actual displacement with respect to the overall displacement. Okay, then I recall you that the overall resistance and the actual resistance are related so that the RA is equal to RP negative RB, very beginning. RA and RB is the potentiometer resistance. Okay, and therefore what you can say is that your RA is just equal to RP, well, negative XA actual divided by total. Okay, now plug this information into the previous one and you have the proof of my first equation, okay, that I'm rewriting just now. So the output tension here is 0 with respect to the feeding or the input tension is given you by this 1 over say xt plus rp over rm and x a xt. Okay. Now, if you remember, we said that in the ideal case, there is a linear relation between the actual unknown displacement and the output tension. What does it mean in this equation, the ideal case? When you are comparing, I'm going back here. Okay. This general circuit, okay. How can you obtain from this one the ideal one? Rm equal to 0.
We don't have any resistance.
But if you are setting Rm equal to 0, then you have a short circuit. Everything flowing there. It is just the opposite. Rm should be infinite. So it is an open circuit. And therefore, you have this one. Yes, this one, open circuit. Nothing else. Okay, so the ideal circuit is the actual circuit in which the measuring device is having a practical large resistance with respect to the potentiometer resistance. Infinite should be. Okay. Second. Yeah. The actual measuring circuit corresponds to the ideal one when the measuring resistance is much larger than the potentiometer resistance. Okay, theoretical should go to infinity values. It should represent an open circuit at the measuring side. Okay, and therefore, if you are setting so, going back to this, so if you are saying that your RP over Rm is going to 0, that is, your measuring resistance is much larger than the potentiometer resistance, okay, then what you're having is that your output tension is equal to the input tension, Ex, okay, times Xa over Xt. It will show. Yeah. Okay. And this value, if you refer to my previous equation, is the constant of proportionality with respect to the actual displacement and the measuring, the output tension, okay, that you are going to measure. Okay. So remember.
No, scusi, quindi quella è la costante di proporzionalità, giusto?
Sì, quella che avevo indicato all'inizio nel caso ideale, senza entrare nel dettaglio.
Ok, grazie.
Ok. Yeah. So your colleague asked that that K is the one that I introduced at the very beginning. Okay. That represents the linearities between what I am measuring and what is the estimated physical variable X. Okay. So I would like to stress the fact that what does it mean, generally speaking, larger, smaller, longer, shorter? You have to be sure to stick to some reference quantity, okay? So to me, for this circuit, for this transducer, the potentiometer, the reference quantity is the potentiometer resistance. So you have to be sure, if you like to work in a sort of ideal case, that the measuring resistance is much larger than the potentiometer resistance. Okay, that is your reference quantity. So larger with respect to what? With respect to the potentiometer resistance. So if your measuring device is characterized by a very large resistance, measuring resistance overall, you don't care about how the measuring device is built. You don't care what's inside. But as long as the measuring device is characterized by a large resistance with respect to the potentiometer resistor, then you can practically see that your transducer behavior is close to the ideal one. Okay?
So even when you say larger though, like if it's like 1 ohm larger, like.
One order of magnitude. So
Okay,
1 or 2 order of magnitude. So if my potentiometer resistance is, let's say, having a 2 ohms potentiometer resistance, and your measuring device is having 200 ohms, then it's not bad. If you have 2,000 ohms, much better. Okay? So the reference is important
so
to
the
be.
ideal circuit resembles.
Yeah, that is the ideal one. So the question is, what happens if we are not in an ideal case or close to the ideal case? So we have that, if you go back here to this equation that I hope that now is showing to the display, yeah, is that there is no linear relation between what you are measuring, the output tension, and what is your unknown physical quantity, the actual displacement. As you can see, you are having sort of non-linear relation between the two. Using such a transducer in that condition, it's very difficult. You would like not to have these operating conditions. Why? Because there is a non-linear relation between what you are measuring and what is the objective of that measurement. And if that is depending on the actual measuring that is unknown, then you are in trouble. That's the reason why we prefer to have linear relations, so that you can skip the operating condition, the reference value, because it is practically the same. Okay. On the contrary, if you're having your measuring device characterized by an electrical resistance that is of the same order of the potentiometer resistance, then the relation is the one that I'm showing you, that is nonlinear. Not good at all from the practical point of view. Yeah.
I think it's just one.
Yeah. Remember, I'm measuring the EO, the E output. Okay. That is what I'm measuring. EX is something that is known. Okay, but the ratio XA over XT is unknown, is your unknown quantity. As you can see, it's non-linear relation. And depends not only on the measure itself, but also the physical quantities that are inside the transducer, RP over M. So it is not a good condition.
But the numerator for that equation is just.
Yeah.
Right, okay.
1 over 1
Just
over.
good.
Yeah. So that's the reason why we try, or we set your measuring chain so that the measuring device is having a large resistance with respect to potentiometer resistance. So you, as engineer that are required to measure the displacement field somehow in a wing, somehow somewhere, okay, you have to know what is your transducer. For example, this potentiometer, good, I'm very happy. The first question is, what is the internal resistance of that potentiometer? And then you have to choose the right measuring device in order to measure the output tension. And be sure about the overall resistance of the measuring device. If these two, potentiometer and measuring device, are 1 order of magnitude difference, measuring device larger than the potentiometer, then you can say that approximately your output tension is a linear relation, the one that is showing here, okay, of your unknown displacement XA. And the constant is the ratio of the input tension divided by the maximum displacement. These are all information that are available from data sheets overall. Okay, so that is the point. What is the error, however, if you are not in the case that you can use measuring device so that resistance is on fast. Okay, the error could be characterized yes, by this chart. Okay, so let me write a diagram like this. X-axis is the ratio of the actual displacement with respect to the maximum, the total displacement. So in this chart, we are ranging from 0 to 1. Let's say 1. And in a y-axis, what we are having is the E0 over the input, the output over the input, okay? The ratio between the measured tension and the input tension, E O over X. As we saw before, in the case of ideal operating conditions, okay, we have a straight line because there is a linear dependency, okay? So, of course, here we are having 1 also there. We can normalize this picture having the same distances, but that is not the case, okay? And so what we are having is okay, straight line, and that is the case where Rp over Rm is going to 0, ideal case, okay? Then, in the case in which the Rm, that is the resistance of the measuring device, is not that large with respect to the potentiometer resistance, then we have a picture. Let me change colors. See? I am emphasizing a little bit, okay? So that we are having here increasing value of the Rp over Rm. Sorry. When I'm using this symbol, then now should appear. I'm saying that the Rp over M is increasing, corresponding to the different curves as the arrow is pointing. Okay. And what we are having is that the deviation between the straight line here is the error. Linearity errors, as it called. Okay. That is what is the error induced by a non-ideal measuring circuit in your measurement. That is representative of the fact that your estimate of the deflection is not in a linear equation, but is a non-linear one. So what you are thinking about your measuring is corrupted by that error. And this error could be proved just by making some calculation. Is the maximum error is about 12% if the potentiometer resistance and the measuring resistance are the same. Okay, it is about, just for your reference, 1.5% if the potentiometer is 1 order of magnitude lower with respect to the measuring device, 0.1 Rm. Okay, so as you can see, when you are operating with a measuring circuit that is not ideal with respect to the potentiometer, okay, then we have the maximum error of about 10%, 12%. Okay, that could be viewed as a large error or small error according to your measurement. Okay, if you are using those measurements for, let's say, assessing a method or assessing a measurement, then maybe it is a large one, error. But if you are using those measurements just to have a rough idea of what's happening, that could be okay. Okay, not that much. Okay. As a general way of operating this kind of transducer, you have to use the larger measuring circuit resistance as possible. Okay, this is why you have to check datasheets and then ask for your service to provide you or a different potentiometer or a different measuring circuit, so that the two resistance are one much larger measuring circuit than the potentiometer one. Okay, so that you are sure that your measurement is not having large measuring errors, as those that I told you. Another point that comes out from that equation is what I call the sensitivity of that potentiometer. How the sensitivity could be defined, sensitivity of a transducer, for example, according to your experience. Yeah, so the sensitivity, generally speaking, is the capability of a transducer of a measuring device to sense small variations of the physical quantity that is going to be measured, okay, with respect to the overall, of course. So with respect to your scale, to your measurement, okay? So the sensitivity is a sort of, let's say, ratio between the change, sorry. With respect to the okay, with respect to the measuring increment. So it's a derivative that is related to your measuring quantity. So the larger is the sensitivity, the better is the capability to distinguish between different values of your unknown quantity. Okay, so yeah, increment that is related to your actual maximum value. Okay, so in our case, the output tension, that is your quantity that you're going to measure, and to which the unknown physical quantity displacement relies to, okay, is a function of your input tension, being constant all the other parameters, that is the potentiometer itself, so the maximum of the value of the potentiometer resistance. So in order to increase the accuracy of the measurement, you can think that you can introduce here, or there, yeah, here, for example, your EX, the input tension, as large as possible, so that the sensitivity of your transducer increases. Okay. So if you are required to measure microns, okay, and you realize that your actual potentiometer could measure without any specific issue millimeters, then you can think that, okay, let's increase the input tension of 1, 2, 3 order of magnitude, so that I can also have the sensitivity, the capability to measure small variations such as microns, okay? That is a way of thinking the problem almost correct, but it is missing an important point. The important point is that you can melt everything. Why? Because if you are feeding your electrical circuit with an increase in input tension, then you have also to think about that because of the Joule effect, there is a heat that is, let's say, coming out from your electrical resistance because of the Joule effect. Okay, so you have to take into account this one. How can you take into account? Just rewriting this equation, just taking into account the maximum power that could be dissipated in your electrical circuit, so that you are not exceeding the maximum power that is not melting anything thanks to the Joule effect. Okay, so let's rewrite that, including also this effect. Okay, yeah. So this maximum power could be written as P max, okay, maximum power that could be dissipated from the
No, mi scusi,
un attimo.
può ripetere un attimo la conseguenza di questo effetto Joule?
Okay. Your friend is asking to repeat this issue. Okay, we saw that the sensitivity could be increased by increasing the input tension. Okay. However, we can't increase this input tension as we like because of the heat that is generated through the Joule effect in your circuit. So we can have, if we increase too much this input tension, we can melt everything because the heat generated is too much to be dissipated from your circuit point of view. Okay, and then we increase temperature.
Ok, grazie.
Okay, so we have to introduce the maximum power that could be dissipated in your circuit, okay, from the Joule effect. How can we do that? Very easy. Remember, the power in electrical circuit is given you by product tension and current, okay, VI, and that is also rewritten in terms of tension and resistance, electrical resistance. Thus, what we can say is that your tension, whatever, could be related to the power and resistance by this equation. Okay, and that is your starting point. Okay, so your maximum input tension EX maximum that could be used in order to increase the sensitivity of your transducer, okay, is given you by root square of maximum power that your circuit is capable to dissipate, okay, times the resistance of your potentiometer RP. Of course, this maximum power depends on the potentiometer configuration. Okay, so you have to check in your data sheet what's happening. Okay.
And so the R that we would use.
Yeah.
R.
Yeah. So you have to check your datasheet, your potentiometer datasheet. You have to check what is your RP in order to set the right measuring device. And also you can see by just making this multiplication and the square, you can see what is the maximum input tension that you can use to feed your measuring circuit in order to achieve the maximum sensitivity. Okay. Generally speaking, for such a transducer, for such a potentiometer that are used in aerospace field, okay, so specially designed for the aerospace application, not for civil engineer, for example, okay, they are larger, bigger, okay, and heavier also. So things that I can use in my aerospace field. The sensitivity S is about 15 volts per millimeters. Oh, sorry, 15, not 15, sorry. Okay. 12. Or if you are using your potentiometer to measure rotation deflection, so degrees, you are having 15 volts per degree. Okay? These are maximum values, of course. Okay? And by the way, generally speaking, your RP, the potentiometer resistance, is of about 100 ohms through 100 kilo ohms. So there is a variety of transducer potentiometers whose internal resistance, the potentiometer resistance, is having a large number of values. Okay, and that is, of course, telling me what is the final sensitivity. So if I have the chance, I can pick the best transducer for my measurement. And just to link this discussion with yesterday's discussion, of course, you have to know an a priori knowledge of what is your measurement. If I need to measure millimeters, microns, meters, okay, you know a priori what you're going to measure, and then I can pick my best measuring device so that I can have the optimal, the best accuracy in my measurements. This transducer is what is called a zero order transducer. What does it mean? That if you think of how is the working principle, what is the equation that is governing this working principle, I am going back for you. For example, this, or whatever, that doesn't matter. No, it's enough. Okay. The square of the lower one. In any case, linear or nonlinear, the equation is a zero order differential equation. Differential equation with respect to what? With respect to time. So this transducer is called zero order transducer with respect to time. That is, there is no delay between the measurement and the actual value of your unknown quantity displacement. Okay? There is no delay. There is no first order, second order in time domain differential equation that is governing this operation of this working principle. Okay? It is just a zero order, no delay. What I'm measuring is just what I have. Okay? If all the measuring devices, that is the potentiometer and the measuring system, okay, are described in terms of resistance as I did. Okay, so no special issues about that. So this is why I can write here the potentiometer is a zero order zero. Okay, that is, there are no issues on time domain response. Okay, please note that this has a very interesting consequence. Why? If you are going to measure what I call a static displacement, okay, this property is not that important. But if you are measuring, for example, the vibration of an operating wing, for example, doing that, then this property, the zero order property, is very interesting because the measurement is not introducing any delay. Okay? Of course, that depends on the frequency of the characteristical frequency of my motion compared to the inertia of my potentiometer. But for what I'm concerned about, low frequency in general for based application up to 1000 hertz, this transducer could be considered as a zero order transducer. Okay, no delays. Another issue. Oh, the question.
So, yeah, perfect. Going back to finding the max voltage that we can apply to the circuit.
Which
So,
one? This
if we're
one?
looking, like, to see how much we can increase the sensitivity by, like, our max value. So we based it off of the potential resistance. And then I guess let's say we look up a chart, right, and you have your max potential resistance. Is a max power value associated with that?
Yeah.
Okay.
I mean, depends on also on your test specimen.
Okay.
Because also the test specimen contributes to the heat transfer. So the same potentiometer could have a maximum dissipated power according to the different test specimen.
Okay.
Okay, if you're placing that in the wood, could be different in a steel, for example. Okay,
So
and also the configuration, the internal configuration of the potentiometer. However, the internal configuration is already known because you can check this information in the data sheet.
Okay, so they're both the max
Yeah.
power and
Yeah, they're telling you the maximum power when attached to, and they are giving you some examples. No. If you go back, that's the reason why I show you. Where is it? Yes. Yes, this one. It's coming through. Okay. If you check the full equation without any approximation, the square one, okay, that is a nonlinear one, but no time differentiation at all. Zero order. Okay. It is nonlinear. That means that there is not a linear relation between the measurement, output tension, and the unknown actual displacement. It depends on many parameters. There is not just one K, okay, that is typical when you are having a measuring device nice from this point of view. Okay. But however, the equation is a very zero order equation from the time domain differentiation point of view. Okay. Yeah. Okay. And, the other point, on the contrary, that I'm telling you right now, is that those potentiometers are very sensitive to the operating condition, to the environment itself. Okay, that's because of the contact. you need to have a contact, a mechanical contact between the internal resistance and the actual displacement. Okay, so what I can say is that the contact between the resistance and the active element okay, what I'm saying is in our model that is the contact, okay, resistance and the element, the mechanical element that is connected to the actual displacement, okay, induce noise. And possible errors. And the measurement depends, and sorry, depends on T temperature. Okay. So we are having a large influence of the external environment because of the contact between the active element and the resistance. This contact is also introducing noise, and because this element is based on the resistance, electrical resistance, there is also an important influence of temperature, operating temperature. Okay, so these items should be included in the overall sensitivity. Okay, maybe you can have, by increasing the input tension, very large, very high sensitivity, but however, we are also measuring a lot of noise. Okay, from the noise point of view, we have to consider friction, okay, humidity, vibration, shocks, unwanted vibrations and shocks. Of course, if you are like to measure vibration, they are wanted, okay? But there could be some noise induced from these unwanted physical operating conditions. Okay, so that is what I would like to know from you about transducer like this potentiometer. So basic facts, operational condition. There is a resistance that could change its value because it's connected to some active elements connected to the displacement, but also rotational. So it's not that difficult to see that. Okay. How can we measure the displacement? Through the measurement of the output tension in an ideal electrical circuit. Okay. However, this is just an idea. So we have to consider also a measuring device. From the measuring point of view, the only electrical parameter that is of interest is the measuring resistance. So no capacity, electrical capacitor, no inductors at all. They are not of interest for our analysis. So just resistance. If that is so, the relation between the output tension and the unknown displacement is not linear. And that is an issue for us. We don't like that. Too much complicated in actual field to take measurement like that. How can we overcome this problem? Just look at the equation. We found out that if you are using a measuring device with a large electrical resistor compared to the transducer resistor, potentiometer resistor, and we are happy because we saw that there is practical linear relation. Not the real one, practical one. And we saw a picture in which we can see that the deviation from linearity is of about 10% when the two resistances are the same. Okay, that is the maximum. Could be large, small, depends on what are you doing, what will you do with those measurements. Okay. From the usage point of view, first, we are happy because it is a zero order transducer. Thanks, we are not considering any inductive impedance nor capacitor, so it's very easy to say that it's zero order. Okay, so the only limitation comes from the inertia of the measuring device, so that could be very high, and therefore we can go up with a very high frequency that could be of interest for our analysis, up to 500, 1000 hertz. Okay. However, environmental effects could be detrimental, like humidity, vibration shocks, undesired vibration shocks, temperatures, brushing contacts that could introduce noise. Okay, that these are the limiting factors. Okay, I think that we can have. I'm sorry to steal your break. No, but you have to tell me so, of course. Okay, right. So let's have no more than 5 minutes break, so that I can keep going and stealing your break, and we end the class with another test. Okay, so 5 minutes. Let's say come back 35.
Prof, mi scusi,
Vai.
avevo alcune domande che ieri non ho potuto fare perché non si prendeva bene la connessione.
Purtroppo ieri è andato e quindi oggi non posso risponderle.
Ah, ok.
No, prego, sto scherzando. Mi dica.
Ma l'esame deve essere sostenuto in inglese?
No, se
Ah,
vuoi
ok.
sì, se vuoi sì, però diciamo che per i doppi lingue come voi, italiano e inglese, potete scegliere la lingua che più vi piace.
Ok, perfetto. E un'altra domanda, invece le lezioni online verranno caricate dove?
Allora, ieri l'ho detto, farò una directory su Drive
Ok,
in cui salverò queste lezioni.
ok, la
E
ringrazio.
voi come utenza, diciamo, di studenti di Sapienza, avete a disposizione da Google uno spazio Drive illimitato. Ecco perché lo faccio, così avete queste lezioni. Le lezioni, peraltro, cercherò di rendere disponibili, diciamo, non per tanto tempo per evitare un uso improprio, e quindi, diciamo, saranno disponibili per circa una settimanella. Ok?
Ok, perfetto, grazie.
Prego. Diciamo, l'obiettivo è quello di mantenere vivo l'operazione di insegnamento, diciamo, in diretta, quindi sincrono. Questo per, come ho detto ieri, per mantenere un pochettino alta l'attenzione, in modo tale che voi siete stimolati a seguire il corso passo passo, e quindi, diciamo, ripristinando quello che era il concetto di faccio lezione in aula e tutto ciò che è da dirci lo diciamo in aula, ci permette anche di apprendere un pochettino, di essere forzati ad apprendere, e quindi questo dovrebbe avere un'efficienza di apprendimento maggiore. Fermo restando ovviamente che, visto le difficoltà tra aula, lezione, eccetera, le lezioni possono essere utili, e quindi però guardatele subito, in modo tale che così, se ci sono dubbi e domande, voi potete chiarirle immediatamente, insomma, entro qualche giorno. Non ha senso, tanto per essere chiaro, che voi fate domande di una lezione che ho tenuto 5 anni fa, insomma, no?
No, mi sembra giusto, mi sembra giusto.
Ok.
E professore, invece, per le prove in laboratorio,
Sto cercando di capire, per le prove in laboratorio cercheremo di fare dei gruppi da 10 persone circa, e faremo delle esperienze di laboratorio. Ovviamente l'esperienza di laboratorio ha senso se si va in laboratorio. L'idea di seguire il laboratorio a distanza non mi piace per nulla, perché significa semplicemente condividere, che ne so, dei file con delle misure, ok?
certo,
Meglio di niente, per carità, però non è questo l'obiettivo. L'obiettivo è proprio quello di farli sporcare e farli cimentare con le classiche problematiche che uno incontra effettuando delle prove, delle misure mirate a un report nel nostro caso, ma mirate a ottenere un certo risultato, a fare certe stime in generale.
certo. E ieri ha parlato di mandare una mail se eravamo appunto, se volevamo dare la nostra adesione per partecipare a queste prove di laboratorio.
Sì, diciamo sì, adesso sto aspettando qualche altro giorno in modo tale che il numero di studenti si assesti, perché sta cambiando un po' alla volta, quindi volevo avere un dato più o meno ufficiale della numerosità e delle persone che partecipano a questo corso. Siamo circa attualmente una quarantina di persone, quindi suddivise in 10 persone abbiamo 4 gruppi. Quindi fra un pochetto vi manderò un'email in cui vi chiederò di distribuirvi nei vari gruppi in modo tale che così ci vedremo in laboratorio la settimana prevista per le lezioni. Per il laboratorio, scusa.
Va bene, grazie mille, professore.
Prego.
Professor, how we can register for as we are attending remotely, how we can register for the groups, and I don't know how we can attend the labs.
Okay, I try to manage a sort of doodle in which I can tell you what are the available groups, and then you can choose the best group according to your activities. Okay, and then the group of course corresponds to a time slot in a day of a week, and then you can choose the best one for you. Generally, previous year courses allow me to say that we can find a solution. If there is no solution for this year, then we can manage to have a solution. Once we got a solution in terms of number of person per group and at each time slot for the day, then we will meet in the laboratory for each group, and then we do our experience in a laboratory.
Okay, sir. And one more thing, actually, because of the bad audio, I didn't understood that examination part. Yesterday, what you have told, the process of examination. Do we have mid exams and all? I didn't heard anything.
I can hear you very well, but if the problem is about the exam, the final exam, yes, the laboratory activities will form, let's say, a sort of report, a group of reports, and then during the final exam, I will ask you something about the report. Okay? For example, laboratory report number 3, what is the outcome and why you have that outcome, for example, something similar.
Okay.
Okay.
Yes, sir. Then we will have details like how we can write the report and all, right?
No, I think that you this year, because of these COVID conditions, you have to submit your report some days before your final exam.
Okay.
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 So you have the time to do whatever you like until some days before the final exam.
Okay. Thank you.
Okay.
Professore, mi scusi,
Prego.
dovrebbe spiegare per favore perché aumentando, diciamo, la differenza di potenziale di X aumenta la sensibilità diciamo, del sistema?
Beh, se lei vede la sensibilità come la derivata dell'output rispetto all'input, lei vede che la sensibilità dipende da X, da EX, quindi dall'input, dalla tensione di input al circuito di misura.
Ah, ok. E quindi aumentando quello aumenta...
Esatto, e quindi la domanda è come faccio ad aumentare la sensibilità? Beh, banalmente posso aumentare la tensione di alimentazione, il che è vero, però entro certi limiti, come abbiamo detto.
Perfetto, va bene. Grazie.
Scusi, professore, una domanda. La sede
Prego.
del laboratorio alla Sapienza oppure su via Salaria? Perché non...
No, è a San Piero in Vincoli.
Ah, ok, grazie.
Bene. È in Palazzina E, dove normalmente vivo.
Ok, grazie. Grazie, professore.
Bene. Are we ready? Let's go. Okay, let's see one different transducer whose aim is, again, to measure displacement. And this transducer is called differential transformer. Okay. Of course, the basic working principle is completely different from the rheostat, from the potentiometer. Okay. And the general layout of this differential transformer is this one that I'm going to write. Now let me see course like this. Okay. This. Okay. Okay, that is the general layout of our differential transformer. So it is composed by mainly three components. We have two coils and a movable core. Okay, this movable core is connected through mechanical connection to the displacement field that we like to have. Okay, so this movable iron, the core, is moving in this picture left to right according to the displacement that we like to measure. Okay, this motion, the motion of this movable iron, is happening inside an electromagnetic field that is induced by the primary coil. Okay, this primary coil is fed by an input tension. And because we are referring to electromagnetic field, this input tension is for sure an alternate current. Okay, its own frequency, its own tension. Okay, now, according to the different position of the iron coil, the secondary windings, the windings, sorry, of the secondary coil will be energized differently according to different position of the iron core. Okay, and that causes different output tension, EO. So just by measuring the output tension is a measuring of how much voltage is energized by the primary coil into the secondary coil, and therefore we have a measure of the position. Okay, so what we are having is that the output tension, EO, depends on the actual position of the movable iron core. And it could be proved, but it's not that difficult to do that if you have some knowledge, basic knowledge on electromagnetic field, is linear, this output tension, with the position of the core. Okay, let me call X position. In your general layout, for example, this.
So it does, it depends on the position of the movable
Yeah.
iron.
Yeah. Now it's showing up the core that is made by iron. Okay.
Okay,
Right.
I see.
Yeah, it is. So we got the X, that is the position of your movable iron, the core of the system. Okay. And that is very nice from the measurement point of view, because once again, we have a linear relation between the unknown position and the quantity, the physical quantity, the electrical physical quantity, the output tension that is going to be measured. Okay, and that is very, very nice. So what we can say is that if we are not entering into many equations about that, but if we plot the dependency of the output tension with respect to the unknown position, so I made this picture in which the x-axis is the unknown position, x, okay, in a given reference frame, and we have EO, the output tension. What we got is something, let's say, like this. Okay, linear, both the first quadrant, that is positive value of both x and E0, okay, and negative values. However, we are in troubles when the position of the core is practically outside of the coils. Okay, so 0 position. Why that? Because if you remember, going back here, the electromagnetic fields, okay, are practically constant inside the core, something like this. Okay, they keep constant if this position is not that different respect to this one. But when you are having the position of the inner core, the movable iron, that is practically outside of the windings, then the windings are no more parallel to the axis of the core, they are whatever, okay? So it is very different with respect to this configuration. And thus the relation between the output tension and the position of the core is no more linear. And thus, this picture has this very bad behavior here, that is around the 0 position. I'm not giving you any scale, but just to tell you that around the 0 position, there could be some issues, no more linear, very strange behavior that is linked to the different path that the electromagnetic field is having when interacting between them and between the iron core. Okay, and this area, this operating condition has to be avoided from the linearly point of view. Okay, linear behavior point of view. Huh? Yeah, oh, sorry. Let's do this. Okay, do that. Okay, avoid that is a D. Okay, in order to reduce that, we have a second avoided, avoid D, no, avoided. This operating condition has to be avoided. Yeah. What? Sorry? It could be millimeters, it could be centimeters. Depends on the size. Yeah. Yeah. Why we want like to have iron? That's the point. Displacement, the x. Yeah. So if you look at that picture, the graph, you are having the output tension E0, to which correspond the unknown displacement field. Okay, x. So the position is giving you your x. So as you saw before when referring to the potentiometer, there is a mechanical link between the iron core and the actual position. Okay. Yeah. 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 Something like that. Could be whatever the origin of this motion. Okay.
I mean, this device can find all of this displacement, or we just find it from torsion bending.
I will remove torsion, but displacement, yes. Displacement. Maybe you can have a vibration like this. Okay. So you have a mechanical connection somehow and then go straight to this differential. Okay. Maybe everything is shrink in just 1 square centimeter. Okay. No. But there is a sensing part that is touching contact, mechanical contact with your structure. And then whatever is in your structure, your contact point will do the same. And will change the internal, yes, the internal position of the coil, of the core, the iron core. Okay. You don't know anything about that. What you will do, what you will know is just the output tension. Just equation, linear equation, you can refer to the unknown displacement just by using this picture. Okay. Come. Go. Okay, the linear one. But however, yes, this one. But however, the zero displacement area should be avoided. Why? Because the electromagnetic field is no more linear when the core is practically outside. Okay, both in the right and the left part, positive or negative part. In order to overcome this issue, we can use the same device, differential transformer, but with a different circuit. Okay, that I show you right now. So the different circuit is something like this. We start again with the movable iron core, like this, that is mechanical connected to your structure as doing whatever motion that you like. There are your windings for the primary core. Okay. But now we have something different. And the circuit is like this. Yes. As you can see, the secondary windings, secondary coils or secondary windings, are connected in a series opposition configuration. Okay, so that the output tension is the difference of the two outputs of the the two voltages. Okay, the secondary windings, write it here. Okay. That is a way of trying to reduce or increase the accuracy of the measurement. However, when you are completely out, okay, of the internal field, inner field, then you can't do anything else. Okay, so that is a reason why we have to use this circuit when the core is just in the middle. Okay, however, this is very nice as a transducer from the measurement point of view because there is a linear relation, both positive and negative. Okay, and that is very, very interesting. Also, this transducer could be viewed as a zero-order transducer. Okay, that is, there are no specific delay. However, in this transducer, because we are making make the use of an iron core that is a component with a relatively large mass compared to the other one, we are using iron, then the inertia is the important factor that is limiting the maximum operating frequency of my unknown displacement that we would like to measure. Okay, and therefore the working principle, the working maximum frequency that we are going to have depends on the inertia of your inner core, okay, and also on the frequency of the input voltage, okay, so that we can say that the maximum frequency, so that we can assume that this transducer is a zero-order transducer, is so that should be less than 1 order of magnitude of the input frequency. That is 1 order of magnitude, 1/10, of the frequency of the EI, the input excitation, the input voltage. Okay? I'm talking about electrical pulse. This transducer, in order to work, requires an alternate current. Okay? Remember, the potentiometer doesn't care. You can use whatever input voltage that you like, continue or alternate. Okay? In this case, for the differential transformer, we need to have, of course, an alternate current. Okay? The frequency of this alternate current is limiting the maximum measurable frequency. And so that the maximum measurable frequency should be less than 1 order of magnitude respect to the input electrical frequency. Okay? And of course, plus the iron core inertia effect, whichever is lower, of course. Okay. Okay, I think that we are done. I steal you about a quarter of an hour, so on Friday I will give you back this quarter of an hour. Okay. Questions? Once they are ready, I put all the recordings in a Google Drive directory, and you, as a Sapienza student, will have practically infinite number of gigabytes available, so that you can use that. And in order to avoid misuse of these recordings, I let you to use these recordings for a week time. Okay, and then I remove them.
Do you have a book?
I'll give these references yesterday.
Oh, okay.
There are the course notes, but however, they are in Italian. There are some chapters already written in English. Some others are in Italian. I share with you this material. Okay.
Okay, so on.
However, these the chapters are, say, available on measurement books. Okay, transducer books. You can find whatever book.
Okay. Do you have one that you can recommend?
Yeah, I gave you that yesterday.
Oh,
So,
okay.
but you can find that on the course website, some references.
Okay.
Okay. Okay. You can
Professor,
yes.
if frequency of core and frequency of alternate current is equal, so what will happen?
Wrong measurements. Oh, wrong measurement. They are not good at all. You have to stay on one order of magnitude difference.
Okay.
Okay.
Thank you.
Okay. I have to leave. So see you Friday. 1P to 2P. Okay. And I'll give you back quarter one. Okay. Thank you. Thank you very much. Now the problem is stop the recording. Yeah. Okay. See.